Okay, so what we're going to do today is we're going to take the review document for Chapter 9, material covered on Exam 5, coming up this next Tuesday. And we're going to look at highlighted problems that I've selected in this document based upon the range of problems. We're not going to do all the problems, just the ones that are representative of all the topics that we've covered in this chapter. And if you want to follow along, of course, this is the key, so it'll have the answers in it. I'm going to show you how those answers are arrived. And then you can also pull up your copy of the worked problems, if you choose, and make notes on that, as the worked problems are how I did it, but maybe during the discussion something else clicks and you want to make a note. So have those ready. You can pause the video and go make yourself a copy. All right, so I selected number 1 first. Number 1. Consider the calcium metal reacts with oxygen gas in air to form calcium oxide. So the controlling equation here is calcium metal, that's solid, plus oxygen in the atmosphere, which means what? Oxygen gas is always diatomic. If you don't remember that, then you cannot write the equation correctly. And makes calcium oxide, which is also a solid. All right. Suppose we react 5.66 moles of calcium with 4 moles of oxygen gas. Right? By the way, first of all, is this equation balanced? Let's check it out. 1 calcium, 1 calcium. Okay. 2 oxygens, 1 oxygen. All right. So you can set up your budget if you want, but usually these types of reactions where you have an element makes a compound are really easy to do without the budget. You need 2 oxygens. Now you have 2 calciums. That's balanced. Now let's look at the problem and see what it gives us. 5.66 moles of calcium. All right. And 4 moles of oxygen. So you may assume that this calcium reaction is not occurring in open atmosphere, right? Some air has been introduced into a vessel where the calcium resides, and this is all the oxygen you have available in the air that's been introduced. So determine the number of moles of oxygen left over after the reaction is complete. What you'll notice is if you're given exact amounts of reactants, both 3, 4, however many, then you can nearly always assume that one of them is going to be limiting. So we have to decide which one is limiting, and the problem gives us a clue. It says how many moles of oxygen are left over, which means that oxygen should be excess and calcium should be limiting. And we can prove it, right? All we have to do is convert this many moles of calcium to calcium oxide. Use our conversion factor. Right, we want calcium oxide in the numerator, calcium in the denominator, and we use the coefficients, 2 and 2. So that's 1 to 1, which means that you should also have 5.66 moles of calcium oxide. But if we convert this one to calcium oxide, we find that oxygen on the bottom, calcium oxide on the top, 2 here, 1 there. We have 8 moles of calcium oxide would be possible if all of the oxygen were consumed. But we see that calcium is limiting. So calcium is going to run out first. That means that this will never happen. This is how much calcium oxide you'll produce, okay? Well, the question is, how much oxygen was required? Since oxygen is excess, we're not going to use all of it. So how much of it did we use? The easiest way to do that is say, okay, if we're going to use all of this, how much oxygen? Right? So you're going to convert calcium into oxygen, mathematically speaking. So we have 2 calciums here and 1 oxygen there. That means 1/2 of 5.66 is, let's see, 2.8, 2.83 moles of oxygen. Okay, let's see, is that 2 times that? 216. Yeah, that's right. So this is all the oxygen that you're going to use. What's left over? Well, it's simple math. Just subtract the 2. Right? That much oxygen remains. Okay? And that's why the answer is A. 1.15 moles of oxygen remain. All right, that was number 1. And it took a long time to do that one because there were several steps, and each step is important. Understanding how we arrive at the answer. All right, so let me scroll it a little bit and get this one on the board. Number 3. Let's move this out of the way. There we go. Sodium and water react according to this equation. Okay, so whoever wrote this question is kind enough to give us the balanced equation. Sodium metal plus water yields what? Sodium hydroxide plus hydrogen. And this is a gas. Sodium hydroxide should be, yes, aqueous. Okay. So if that's the balanced equation, what else are we given? What number of moles of hydrogen will be produced when 4 moles of sodium is added to 1.2 moles of water? And the answer to the question is how many moles here? So that lays out that word problem in a form that's more recognizable. This can be solved. We're given amounts of sodium and water, which means more than likely one of them will run out, will be limiting. So we have to determine which one is limiting. Well, let's take this one first. If we have 4 moles of sodium, how much hydrogen can we produce? If we use all of it, well, the ratio is 2 sodiums to 1 hydrogen, which means we could produce as much as 2 moles of hydrogen. Oops. 2 moles of hydrogen if all the sodium is used. What if all of the water is used? We just need to convert water to hydrogen. 1 here and 2 there. So this would be 0.6 moles of hydrogen could be produced. Right? Obviously, water is limiting. And we're not going to produce that much because sodium is excess. So this answers our question. 0.6 moles of hydrogen will be produced from that reaction, and the quantity is given. Let's see, can we get both of those? No, we're going to have to do 5 is next. All right, 5. In the reaction, nitrogen plus hydrogen yields ammonia. This is your Haber-Bosch process. N2 plus hydrogen yields ammonia. All right, and let's see, 2 here and 3 there. Yes. Okay, how many moles of ammonia would be produced from 1.21 moles of hydrogen? And they're telling us that the nitrogen is excess. Okay, so we don't have to determine which one runs out. We're going to use up all of the hydrogen. And how many moles of ammonia are produced? Right? This is a simple one-step calculation. Hydrogens cancel, leaves us with ammonia, and the ratio is coefficients. So 2/3 of that, of 1.21, will give us our answer. 1.21, 2 times 3 divide. Let's see, 3 significant figures. I've got 0.8067. All right, so we have to chop it down to 3 significant figures. All right, so C is the answer, 0.807. These first 3 problems are similar. Right? There were some nuances to each one, but it does give you a good bit of practice in how to recognize the steps that are required to get to the answer. Now, some of them take 1 step, some take 2, some take 3. Break your problem down into small chunks. Okay, this question actually tells you that this reaction is not balanced. So we need to balance it first. Let's do that. C2H5. Let's see, we're number 6. Okay. C2H5OH plus what? Combustion, oxygen. I'm going to leave out the states of matter in this case because we don't need them, and it just gives us some extra room. Okay, so set up our budget. We have carbon, hydrogen, and oxygen. That's it. So we have 2 carbons on this side. We have 5, 6 hydrogens, and we have 2, 3 oxygens. Then on the other side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay. So now, where do you start? Well, we definitely don't want to start with oxygen because we want to hold that one to the end, right? So, elements, we hold to the end. So let's do carbon. How about carbon? We need 2 carbons. All right. That changes the oxygens to 4 plus 1 is 5. Okay. So how about hydrogens? Right? We need 6 hydrogens on this side, don't we? So that's 6 hydrogens. Okay? But it also changes to 3 plus 4 is 7 oxygens. Okay. Now here's the little tricky part. Oxygen occurs here, but it also occurs there. And you need 7 oxygens. But you've already got 1 here. So this could deliver 6 oxygens and you'd be perfectly fine. It'd be 6 plus 1 is 7. So how do you get 6 oxygens out of this? Just multiply by 3. And that gives you 7. 6 plus 1 is 7. So now we're balanced. That's our first step. Okay, next. What are we given? 1.7 grams of ethanol, 1.70 grams of ethanol, and 11.2 grams of oxygen. Okay, now the question is, how many moles of carbon dioxide are produced? How many moles? All right. Notice you're given exact amounts of each one, but neither one of them is moles. So the first thing we have to do is convert each of these reactants to moles. Then we can determine which one is limiting. So the next step is convert to moles. So what's the molar mass of this one? Well, let's see. We need 2 times 12.01 for carbon, and we need 6 times 1.01 for hydrogen, and then 1 oxygen. Right? So let's add those together and find out what the molar mass of ethanol happens to be. .08 grams per mole. All right, so let's take this one, grams of ethanol, and convert it to moles. All right, grams on top, grams on the bottom, cancel. 46.08. So how many moles of ethanol do we have? 0.0369 moles of ethanol. That's my abbreviation for ethanol. Now we want to find out, since we're here, let's go ahead and find out how many moles of carbon dioxide could be produced if all of the ethanol is consumed. So we have moles of ethanol and moles of CO2. The ratio is 2 here and 1 there. So we need 2 times that value, 0.738. That's the amount that could be produced from that much ethanol. Now we knew oxygen. Right? So we have 11.2 grams of oxygen. Right? 2 oxygens, 16 for each, 32 for total. So 32 grams of oxygen per mole gives us how many moles? Let's see, 11.2 and 32 divided. 0.350 is moles of oxygen. Now let's find out how much CO2 can be produced. CO2 is still 2 here, and oxygen is 3 there. So 2/3 of that value would give us 0.2333 moles of CO2. Okay, so this is going to be the limiting. This is limiting. That means we're going to use this. That's our answer. let's see, we have 3 significant figures. There we go. 0.0738. So there, E. E is the answer. All right. That's number 6. All right, number 7. Let's see here. Fe2O3, and they give you the molar mass, reacts with carbon monoxide. According to this equation, Fe2O3 plus 3CO. And it produces what? CO2 and iron. All right. 2 of these. There we go. All right. So, by the way, what's that? What's this called? That's carbon monoxide, carbon dioxide. Those are easy. How about this one? -2 here, -6 total, +6 total here to balance means this is +3. So this is iron 3 oxide. Okay. Just a refresher. All right. So the question is, when you have 185.5 grams of CO, 185.5 grams of carbon monoxide reacts with excess. That's nice. So we're going to use all that up completely. How many moles of iron will be produced? Notice in this word problem, if I haven't said it before, word problems are designed to confuse. Because if you do not understand all the basic concepts that go into solving a problem, the word problem will confuse you. You will not know what to do. If you are well practiced in these types of problems, then what you'll do is you'll pick out the information that you need. First of all, the equation, then the given information here. One of the pieces of given information is the molar mass of Fe2O3. Do we need it? No. It's excess. We're only going to work our problem based upon this one. So we need to know the molar mass of this one. How many moles of iron will be produced? Right? So we have to calculate the molar mass of carbon monoxide, which should be 16 for oxygen and 12.01 for carbon. 28.01. So 185 grams, 185.5 grams of carbon monoxide is going to yield 28.01 divided into that. 185.5 divided by 28.01. 6.6226. That's moles of carbon monoxide. Then we convert moles of carbon monoxide to iron using the coefficients as our conversion factor. Right. Carbon monoxide would be 3, iron would be 2. So 2/3 of that value will give us our answer. 4.4151. Let's see, how many significant figures? 4. So we have to round it. There we go. 4.415 moles of iron will be produced from this balanced equation and this amount of carbon monoxide with excess iron 3 oxide. All right. Let's see what's next. We'll skip a few. There we go. How about this one? The following equation, 4 ammonias and 7 oxygens. Let's see, that's number 10. 4 ammonia, 7 oxygens yields 4 nitrogen dioxide plus 6 water. There we go. Now this should be balanced. Let's check. 4 nitrogens, yep. 12 hydrogens, yeah. 14 oxygens. That's 8 plus 6 is 14. Okay, we are balanced. Now we can go to the next step. How many moles of ammonia will be required? How many moles of ammonia will be required to produce 11.9 moles of water? Now, it does not tell us that oxygen is in excess, but we have to assume that. If oxygen is not in excess, then we don't know when the reaction stops. So the only way to solve the problem is to assume that all of that ammonia will be consumed and produce water. Okay, so now we can work backwards, right? As long as you're in moles, you can move anywhere in a balanced equation and determine amounts of any of the reactants or products. So if we have 11.9 moles of water, then all we have to do is set up our conversion factor to get rid of water, the denominator, and leave us with ammonia. 6 water and 4 ammonia. So let's see what that is. 11.9. Actually, it's 2/3. 4/6 is 2/3. Is 7.9333. Okay, but we only have 3 significant figures, so we have to chop it off right there. So that's how many moles of water, ammonia, are required to produce that many moles of water. Okay, that was fairly simple. Number 10. Okay, just a second. Okay. What's next? After 10, we skip to 13. All right, consider the following unbalanced equation. Okay, Na2SiF6. Na2SiF6 plus sodium yields silicon and sodium fluoride. Yes. Okay. All right, we need to balance this equation. All right. So let's set up our budget just to be safe. We've got sodium, silicon, and fluorine. That's it. 3 sodiums, 1 silicon, 6 fluorines. On this side, we have 1 sodium, 1 silicon, and 1 fluorine. Okay, where do we start? Well, we want to hold the sodiums till last because we've got this individual here. So let's go to fluorine. So if we've got 6 fluorines, we want 6 fluorines there, which changes the sodium to 6. Now, notice that since sodium is in 2 different places, we need 6 sodiums, but we've already got 2 here. So 2 from 6 is 4. And that should balance it. Let's see if it does. 2 plus 4 is 6. 1 silicon, 1 silicon. 6 fluorine, 6 fluorine, 6 fluorine. And 6 sodium here. Okay, we're balanced. Now we can work the problem. All right. Let's see, if 3.09 moles of silicon were produced, okay, from a reaction, how many moles of sodium fluoride were also created? In this case, we just have to assume that since this is produced, then the ratio of this one to this one determines how much sodium fluoride is produced. So all we have to do here is convert this one to sodium fluoride, silicon, sodium fluoride, and the ratio is 6 here and 1 there. So 6 times 3.09 is 18.54. Well, 3 significant figures. We have to round it off. There we go. 18.5. That's why A is the answer. And notice that one of the answers there is B, impossible to determine without the moles of reactants. It doesn't matter. Once the equation is balanced, based upon the question itself, the question didn't say how much reactant. It just said how much product is produced if this product is that amount. It's a simple conversion factor problem. All right. 13. Next one, let's see, 18. Okay. How many atoms of aluminum can be produced by the decomposition of 31.5 grams of aluminum 2 oxide? All right. This one, you need to understand what decomposition means. Al2O3, aluminum 3 oxide, Al2O3, decomposition will produce elements, aluminum over here, and oxygen in its most stable form, which is O2. All right, this will be a solid, this will be a gas, of course, and this is a solid. Now we need to balance the equation. Right? This is easy. 2 aluminums, 2 aluminums, 3 oxygens, we need, use our fraction trick. 3 halves of oxygens gives you 3 oxygens. And then we say 2 to get rid of that fraction. So that means there'll be a 2 here, there'll be a 4 here, and there'll be a 3 there. Okay? So now our balanced equation, leave that 2 there. Let's clean it up. Put our 4 here. And then our 3 is still here. There we go. Now that's our balanced equation. If you can't do that, first of all, if you don't know what decomposition means, or if you cannot balance the equation, then you cannot answer the question. Now it says 31.5 grams of aluminum oxide. Yeah, 31.5 grams of aluminum oxide. How many atoms of aluminum? So we want to know atoms, number of atoms of aluminum that can be produced. Okay, first of all, this has to be moles. You cannot move from here to there without moles. So we need 31.5 grams. Right. We need the molar mass of aluminum, aluminum oxide. So let's see, 2 aluminums, 2698, 2698, 2 aluminums, and 3 oxygens. There we go. So let's calculate that one. It's not given to us, I don't think. No, it's not given. So 26.98 times 2, and then 16 times 3 is 48. Add that together. 101.96. So we have 101.96 divided into 31.5 is 0.3089 moles of aluminum oxide. Okay, so how many moles of aluminum are produced? Right. Let's see, we got a coefficient for aluminum is 4, and the coefficient for aluminum oxide is 2. So just 2 times that, right? 4 divided by 2 is 2. Would be 0.6179 moles of aluminum produced. Now we need atoms. What's the conversion factor for atoms and moles? Avogadro's number. So we just need to multiply that times 6.022 exponent 23 times. So that gives us 3.7209 times 10 to the 23rd atoms. Significant figures, 3. So we got to round it off to here. 3.72 times 10 to the 23rd atoms. That's why the answer is A. All right, 18. Who's next? There we go. Number 23. Calculate the mass of water produced when 9.47 grams of methane reacts with an excess of oxygen in the following unbalanced equation. So we're going to combust methane in excess oxygen. And it's going to produce carbon dioxide, and water. Okay. So to balance the equation, do we need to do the budget? To be safe, carbon, hydrogen, oxygen covers them all. 1 carbon, 4 hydrogens, 2 oxygens here, 1 carbon, 2 hydrogens, and 3 oxygens. Okay. This looks like we might be setting ourselves up for a problem. That's even and that's odd. But don't fret yet. Let's work on a problem. We're not going to do oxygens first anyway. So let's work on carbon and hydrogen. Right? Carbon's okay. So let's work on hydrogen. 4 hydrogens here. We need 4 on this side. Right? There's 4 hydrogens. That changes to 4 oxygens. Right? 2 plus 2 is 4. So we need, excuse me, we need 4 oxygens on this side. A 2 will do it. And we can see from our budget that everything's balanced. Now we can move with the chemical quantities, or what we often call stoichiometry. Right, we're given 9.47 grams of methane. Okay, and excess oxygen. All right, and the question is, what's the mass of water produced? So how many grams of water will be produced? So remember, you can't go anywhere in this equation as long as your mass. You got to convert to moles. So what we need is a molar mass for methane, right? 12.01 for carbon and 4.04 for hydrogen, because it's 4 times 1.01. 1605. So now we can convert that many grams of methane into moles. 16.05. So how many moles of methane are we talking about here? 9.47 and divided by 16.05. 0.5900. That's how many moles of methane. So we're going to convert that to moles of water using the coefficients, right? 2 here and 1 there. So 2 times that value will be the moles of water produced. 1.1801. That's because the number that my calculator showed me didn't show me all the digits that were available, and I just left it in my calculator and multiplied by 2. So any of these over here were factored into that calculation. That's how many moles of water. Now we got to convert that to grams. Oops. Grams goes on top. Moles on the bottom, because we want to cancel these moles. So what's the molar mass of water? We've done that so many times, we ought to have it memorized. 18.02. Okay, so 18.02 times that value is 21.2647. Grams. Let's see, we're working with 3 significant figures. So it'll be 21.3 grams. That's why the answer is E. Okay, next. 26, unbalanced equation. All right, so we got to balance this one. AO4C3. Let's see, problem number 26. Al4C3. By the way, that is aluminum carbide plus water yields what? Aluminum hydroxide. Plus methane. Okay, so now we have to balance it. I think we ought to use the budget simply because we've got this polyatomic ion here, and we've got this complexities here. I think it'll be safer to use a budget. So we've got aluminum, carbon, hydrogen, and oxygen are our elements. On this side, we have 4 aluminum, we have 3 carbon, 2 hydrogen, and 1 oxygen. On this side, we have 1 aluminum, we have 1 carbon, hydrogens. We have 4 plus 3 is 7, 7 hydrogens, and 3 oxygens. Okay. All right, where do we start? Well, we don't have any simple elements, so we can't hold those in reserve. We've got, those are all in one compound, carbon, aluminum, hydrogen, oxygen, separate. Aluminum, oxygen, hydrogen, and hydrogen over here in 2 different places. So let's see. What if we'd have to use a fraction to get that one to work? So let's do the carbon first. Okay. Yeah, we can do the aluminum first. It really doesn't matter. Okay, do aluminum first. So we need 4 aluminums over here. Okay, that will change the oxygens to 4 times 3 is 12. And it'll change the hydrogens. 4 times 3 is 12, plus 4 is 16. 16 hydrogens. Okay. How about carbon? Now we need 3 carbons on this side. Right? So that gives us 3, but that changes hydrogens again. So 4 times 3 is 12 hydrogen, and 3 times 4 is 12. So we have 24 hydrogens. 24 hydrogens. Okay. Now we have 24 hydrogens and 12 oxygens. Notice the ratio here is 2 to 1. And the ratio here is 2 to 1. And the ratio here is 2 to 1. If we put a 12 right there, that will give us 12 oxygens and 24 hydrogens. And we're balanced. Okay, now we can work the rest of the problem. Which is, how many moles of water are needed? How many moles of water are needed to react with 206 grams of aluminum carbide? 206 grams of aluminum carbide. Okay, so what they're saying is, as far as you're concerned, this is excess. We can go as high as we need to be to use up all of that. So we're going to have to convert this to moles, right? So we got to calculate aluminum carbide molar mass. So it's 4 times aluminum, which is 26.98. And then 3 carbons, 12.01. Right? So I can't do that one in my head. 26.98 4 times, and then 12.01 times 3, and add those together. 143.95 grams per mole. So 206 grams of aluminum carbide, we're going to find out how many moles that represents with this conversion factor. That's kind of sloppy. Let me fix that. 143.95 grams per mole. Okay, we're going to divide that into 206. So that's 1.4311 moles of aluminum carbide. Okay. So we want to convert that to moles of water. And the ratio is one of these and 12 of those. So 12 times that value should give us our answer. 17.1726 moles of water. But we've got three significant figures. So we got to round it down, 7.2 moles of water. 17.2. That's why the answer is B. All right. Who's next? 29. Oh, okay. I was just looking at that in the blue is a separate problem entirely. We're just going to work the 29 for now. All right. So if we're given this balanced equation and X is an unknown element, so we have 6X, which is a solid, and we're going to add to that diborane, 2B2O3, which is also a solid. Excuse me. Yes, that's a solid. And that yields tetraboron tri-X. Okay, that's a solid. And we get 3XO2. That's a gas. Okay, so there's our balanced equation. And we're told that we have 165 grams of X reacts completely with diboron trioxide. 165 grams. This reacts completely with diboron trioxide, which means that this is excess. There's plenty of it. To produce 2.29 moles, 2.29 moles of that product. What's the identity of X? So what's X? All right. X is an element. How do we determine an element? What are the clues for finding what an element is? You have two possibilities. One is the atomic number, the number of protons, the Z number. If you know that, you can go to the periodic table and find the Z number, the atomic number, and that'll tell you the element. But we don't have access to that. There's no way to get it from this problem. Our other option is determine the molar mass of the element. And that is very often just as unique as the atomic number. There are places in the periodic table where they're very close together, so experimental error could cause them to overlap. And then you'd need a tiebreaker. But most of the time, the molar masses of the elements are sufficiently different from one another that you can identify them based upon that value also. So what do we need to know to calculate the molar mass? Right? This is my abbreviation for a molar mass, molecular weight. Molar mass is the mass of the element per mole. So we need to know the mass and the moles. We got the mass right there. We just need to find out how many moles does that represent. Okay? Fortunately, this is a balanced equation, and we're given this many moles of product. So we can find out how many moles of that by converting this many moles to that many moles. Right? Of this compound. Now we can convert V4X3 to X. This is 1, this is 6. So the number of moles is just 6 times 2.29. 13.74. That's how many moles of X. So we can calculate the molar mass as 165 grams divided by 13.74 moles. All right, 165 and divide that number into it. We get 12.0087 grams per mole. And let's see, 3 significant figures equals 12.0. Right? We have to chop it off right there. Grams per mole. So you go to the periodic table and you look, you follow along from top to bottom, left to right, as the molar masses increase, and you stop when you get to the one that's close to this one. And as it turns out, this is carbon. X is carbon. Okay? All right. Now let me see, what did I put that? What was I trying to do with that blue? Okay, I'm game. X plus 3F2. X plus 3F2 yields what? XF6. Okay. What are we given? X is 235.2 grams. 235.2 grams. Okay, that's good. XF is 347.9 grams. Okay. All right, what's X? This one's a little more difficult. Let me see. We need to find out how many moles this represents. So, here's the trick. Remember the conservation of mass in a chemical reaction. That law was proposed by Antoine Lavoisier and was proven correct by experiment and was explained actually by Dalton's law of atomic theory. This is the total mass. This is the mass of that component. What's the mass of that one? The mass of this one is 347.9 minus 235.2. Right? 0.7211. That's how many grams of F2 were required, right? Because the mass on this side has to equal the mass on that side. Now we've got the mass of something we can calculate moles from, right? So we can say this one, grams here, moles there. We just need, what's the molar mass of F2? Well, it's 2 times 19 or 38. Right? So 38 into a 112.7 is 2.9658. 2.9658 moles of F2. Now that we know the moles of that, X is just a third of that, right? F2 here, coefficient there, and coefficient there. Okay, so 3 divided into that gives us moles of X. 9886. 0.9886 moles of X. All right, now the molar mass of X is 235.2 grams per 0.9886 moles. So 235.2, yep, divided by that number is 237.9. 237.9 grams per mole. Yeah, 4 significant figures, we're good. Now we got to go find out what element has that molar mass, 237.9. That's a heavy element. So we move way down at the bottom of our chart and we find that the closest one, all right, we got the possibility of 2 different ones. It could be uranium or it could be plutonium. Yeah, let me see if I have a value for plutonium. Plutonium on the chart only gives you the most stable isotope. Oh, excuse me, not plutonium, neptunium. Actually, neptunium is 237.048. It's not plutonium. Neptunium is 237.048. Yeah, I think this is it. Excuse me, that's nitrogen, that's neptunium, NP. So I think that is our element, neptunium. Okay. That was just a little extra. That wasn't in the review document. But it gave you a taste of what you can do. All right, number 32. Which of the following reaction mixtures would produce the greatest amount of product, assuming all went to completion? Each involves the reaction symbolized by the equation N2,3H2 yields to ammonias. Okay, so what are our choices? A is 1 mole of nitrogen, 3 moles of hydrogen. 1 mole, 3 moles. Let's just put them all up here and then we'll talk about them. 5 and 3. 5 and 3. C, all would produce the same amount. Same amount. Okay. D, which is another way of saying all of the above. 1 mole plus 6 moles. 1 plus 6. E is 3 and 3. 3 and 3. Okay, and back to the question. Which of the following would produce the greatest amount of product? So we want the greatest amount here. All right. So if we have one of these and 3 of these, that is what we call a stoichiometric mixture. It's only going to produce 2 moles of that product. If we have 3 here and 5 there, that simply means that nitrogen is in excess. We only need 1 of them, and we're going to have 4 excess. So 3 and 5, 3 with 5 still only produces 2 moles because hydrogen runs out. Okay, how about this one? 1 and 6. Well, we got 1 here, and we only need 3 of those. So we have 3 excess. And 1 of these produces 2 of those. Let's see, 3 of these and 3 of those. This one needs 1 of these. So we have 2 excess. This also produces 2 moles. That means C is the answer. They all produce exactly the same amount of product. All right. That was 32, 33. The balanced equation, phosphorus plus hydrogen yields phosphorus trihydride, tells us that 5 moles of hydrogen, what? Okay, let's put the equation up here. So we got P4 plus 3H2, is it? No, 6H2. 6H2 yields 4 PH3. Let's see, is that correct? 4, 4, 12, 12. Okay, we're good. 5 moles of H2. If we have 5 moles of H2, now it doesn't say, the balanced equation tells us that 5 moles of H2 cannot react with phosphorus. We've got the equation there. We know it reacts with phosphorus. Reacts with how much P4? Okay. Produces, well, I'm looking at the answers to guide me in the direction. So if we calculate the moles of P4, we calculate the moles of pH3, then we'll be able to answer. So if we say 5 moles of this produces how much product? Okay, so we've got H2 and pH3. We got 4 here, 6 there. So 2/3 of 5 is 3.333. 3.33, well, round it off, 3.3 moles of pH3. And then how much P4 would be required? H2 cancels. P4 is 1, that's 6. So 5 divided by 6 is 0.833. 0.833 moles of P4 are required. Rounded off is 0.83. There we go. Now we can look at our answers. B, reacts with 2.5 moles of P4. No. Produces 3.3 moles of pH3. There you go. That's your answer. The rest of them are wrong. We found our answer right here. That's C. All right. Here we go. Next. Okay. Let me do a quick look-see and see how many more we got. 39. We got a few more, but we have to skip a lot because there's a lot of repetition. So let's do 39. Consider the reaction of magnesium metal with hydrochloric acid. Magnesium metal with hydrochloric acid to yield what? Well, I know what it's going to yield, but the problem tells you also. Magnesium chloride and hydrogen gas. Magnesium chloride, which is in solution, and hydrogen gas. That has to be diatomic. And this one has to be written correctly also. Halogens, -1. Alkaline earths, +2. That means we need a 2 right there. That's the first problem. Write your compounds and your elements correctly. Now balance the equation. All right. We got a magnesium here, magnesium here. We need 2 chlorides, 2 chlorides. That gives us 2 hydrogens, 2 hydrogens. That one was easy. Now it's balanced. How many moles of hydrogen can be produced if 4.52 moles of magnesium react with 4.52 moles of hydrochloric acid? How many moles of hydrogen? Yes. All right. The hard part for this one, I think, is getting the equation right. Once you got the equation right, now we can find out which one is limiting. Right? 4.52 moles of magnesium could potentially produce how much hydrogen gas? Well, the coefficient is 1 there and 1 there, so it could produce 4.52 moles of hydrogen gas. 4.52 moles of HCl is a different ratio. Right? We got a 1 here and a 2 there. So 2 divided into that would be 2.26 moles of hydrogen gas. Okay, there's your limiting. This is limiting. This is excess. Right? So that's how many moles can be produced of hydrogen gas from that combination in that reaction. So the answer is C. All right. Let's see. I think we got a long dry spell in here. Oh, there we go. 43. With the following balanced equation, and you can check it out for yourself, but it appears to be balanced. 4 ammonia, 7 oxygen. 4 ammonia plus 7 oxygen yields what? What are we doing? We're burning ammonia. It's a combustion reaction. 4 NO2 plus 6 water. Okay. How many molecules of water are produced? Molecules of water. If 9.19 moles of NO2 are given off, 9.12 moles are given off. All right, so we need to convert NO2 to water. And the coefficients tell us the ratio, 4 there, 6 there. So 9.12 times 6 divided by 4. 13.68. 13.68 moles of water. Okay, now we need to convert that to molecules. So moles of water are ratioed to molecules by Avogadro's number. Okay, so let's multiply Avogadro's number times that. There. And let's see, significant figures. We have 3. So I'm going to round it off to 8.24 times 10 to the 23rd molecules. Uh, 23rd. Oh, my mistake. 24. There we go. So that answer is D. Okay. Let's search for another one. Here we go. 45. Pin 2 fluoride is added to some dental products to help prevent cavities. Pure fluff. Who cares, right? That doesn't even ask the question. Manufacturers have to make the tin 2 fluoride first before they can add it to their products. Okay, now we get to the meat of the problem. Tin metal is reacted with what? Hydrofluoric acid. All right. To produce tin 2 fluoride. And hydrogen gas. Okay. And okay, well, let's see, is that aqueous? Yeah, it's aqueous. Since we started it over here, we need to be consistent. Okay, is that balanced, first of all? 110, 110. 2 hydrogens, 2 hydrogens. 2 fluorines, 2 fluorines. It's balanced. How many grams of tin 2 fluoride can be made from 49.6 grams? 49.6 grams of HF. How many grams of this product? If there's plenty of tin, so they're saying excess. All right, so we got to convert this into moles before we can move over there. What's the molar mass of HF? Well, let's see. Fluorine is 19 and hydrogen is 1.01. So that's 20.01. 20.01 there. So we divide 49.6 by 20.01 and we get 2.4788 moles of HF. Notice I keep all my decimals so that I avoid rounding errors. Okay, so how many moles of tin 2 fluoride are produced? Well, here's the conversion factor. There's 2 there and there's 1 there. That means we divide that value by 2. 1.2394. moles of SNF2. Now we need to convert that back to mass. We need molar mass of 10,2-fluoride. Okay, so 10 is pretty heavy, 118.71. That's 10. And 2 fluorines is 2 times 19. Or does it tell us in the problem? No, it doesn't. We have to calculate it ourselves. Okay. So 10 is 2 times 19 is 38. And then 118.71 is 156.71 grams per mole. And then multiply that, because those cancel, multiply that times 1.2394. And that's 194.2233 grams. Well, we rounded off 3 places. 194 grams of 10,2-fluoride can be produced from that many grams of hydrofluoric acid. Okay? There we go. All right, what's next? And we got some to skip. You'll notice occasionally I've got some blank ones in here. What I determined was that the problem set from which I was working covered material that you had no way of knowing and answering the question. So, and I'd already written out the worked problems in hand, by hand. And I didn't want to have to go redo them and renumber them, so I just cut those out. All right, where's another yellow one? Okay, we got a bunch of repeats in here. There we go. There's a new one. So let's do that one. Consider the following reaction, number 60. (2A plus B) yields 3C plus a D. 3C plus a D. All right. Obviously, these are not real compounds or real elements. So we're working hypothetically. So we're given 3.35 moles of A and how much B? 2 moles of B. All right. React to form 4 moles of C. Okay. What's the percent yield of this reaction? Okay. I know what you're probably thinking. When we discussed percent yield in class, in the lecture, we were working in terms of mass of theoretical product in the denominator, and in the numerator was the actual mass, right? In this case, we have no way of telling the mass. So the only way that we can approach this problem is mole ratio. What's the percent yield mole ratio? All right. So this is actual. It says that was actually produced. What would be the theoretical? Well, we've got actual amounts here, so what we need to do is find out which one's limiting. Right? We can do that the hard way, right? Which is okay. Right? If we have 3.35 moles of A, how much C would that produce? A, C. C is 3, A is 2. So 3.35 times 3 divided by 2 is the wrong answer. 3.35 times 3 again, divided by 2. There we go. 32.4. No, 3.24. Right? What did I do wrong? 3.35. 3 times 2 divided. That's not even the right answer. The right answer is 5.03. That doesn't make any sense. Because the first answer I put up there was in the neighborhood of this one, and we multiplied by 1.5. So this is the answer. So this would produce that many moles of C. How about this one? Moles of B would produce what? 1B here and 3C here. So 3 times that would be 6. Right? This is the limiting reactant right here, limiting. And that means that this is the theoretical amount. So the actual divided by the theoretical times 100 would be a calculation of our yield. $79.5. Yeah, that's what I got. 79.5% yield. The closest answer to that one is D, 79.6. When you have multiple choice and there are no special ones in there, like none of the above or 2 of the above or whatever, then pick the best answer. And the best answer here is D. There's some rounding error in there, I'm sure. Okay, that's 60. Let's see, and scroll a little bit. Oh, 61. Okay. 61. Calculate the molecules of oxygen required to react with 25 grams of sulfur in the following reaction. So we have 2 sulfurs and 3 oxygens. Yields what? Sulfur trioxide. Let's see, 2 sulfur, 6 oxygens, that's good. Okay, and we're given, we want the molecules of oxygen required. Molecules of oxygen required to react with 25 grams of sulfur. Okay. So we got to have this in moles before we can move from here to here. So we need 25 grams of sulfur converted to moles. Sulfur is 32.07. So 25 divided by 32.07 is 7795. That's how many moles of sulfur. So now we're going to convert moles of sulfur to oxygen. Right? And the ratio is 2 of these, 3 of those. And so 1.5 times that is 1.1693 moles of oxygen. Now we need molecules of oxygen. Right? So the magic number here is again Avogadro's number. So let's take that number, plug in Avogadro's number. And that's let's see, three significant figures, 7.04 times 10 to the 23rd. Molecules of oxygen. That would be D. Okay, continuing on. '69. In the reaction between carbon monoxide and Fe3O4, the theoretical yield in an experiment is calculated to be 47.2 grams. Then we're given the actual yield. In fact, you don't even need to write the equation for this one. The theoretical yield is calculated to be 47.2 grams of iron is a theoretical. The actual yield from this careless student is 37 grams. Right? So 37 divided by 47.2 times 100 is 78, three significant figures, 78.4% yield. That's D. Notice Fe3O4. Fe3O4. I didn't try to name that compound because I already know that this is kind of squirrely, right? If you try to calculate the charge on iron, look what you come up with. -2 here, -8. This has to be +8. So +8 divided by 3 is not a whole number charge for iron. What they've discovered is Fe3O4 is a composite of two compounds. Let's see, this would be 2 times 3 is 6. Yeah, 6 2/3. 2 2/3 would be the charge. So this is somewhere between 2 and 3. So what you need is two compounds, one of them with a charge of 2 and the other one with a charge of 3. So this would be FeO, that would be perfect, just like that. And this one would be 3 here and 2 there, Fe2O3. So this formula is a composite of those two. You don't have to know that. That's just an interesting fact. And that's why I was unable to name that compound for you, because it just wouldn't work. Unless you, right, Roman numerals don't come in fractions. Right? So when we put the Roman numeral charge next to the name iron, we can't use a fractional Roman numeral. So I couldn't name it for you. All right, how about 70? 70, 3.1 mole sample of potassium chlorate was decomposed according to this equation. How many moles of oxygen are formed, assuming 100% yield? Okay, let's write the equation. 2 ClO3 decomposes, correct, into potassium chloride plus oxygen. Yes, 3 oxygens. Okay. This will go into solution, right, readily. So what you do, if you're a devious chemistry student, is you take a concentrated solution of potassium chlorate and mix it up, and then you take droppers and you drop it on the floor in the lab, and it dries into little white spots that are hard to detect in most tile floors. So when the teaching assistant, the lab assistant, or even the professor comes in, walks around, they step on those things, and all they need is a little pressure from their foot on that compound, and it will decompose by this reaction. And it produces a lot of oxygen in the process, which is the popping sound. And when they step, it'll pop under their feet and give them a sensation, but it's not hazardous. Okay. Now, I'm not telling you to do that, right? You shouldn't do things like that in the lab. How many moles of oxygen are formed with 100% yield? If we're starting off with 3.1 moles of potassium chlorate. Okay. Moles of oxygen. All right. So this doesn't even have a limiting reactant, right? Because it's a decomposition of one compound, right? So all of it is consumed. So what we need is KClO3 here and oxygen here. That's a 3 and that's a 2. So 1.5 times 3.1 is 4.65 rounded off, 4.7 moles of oxygen. That would be E. 71. When 3.4 moles of iron react with chlorine, probably a gas, according to this equation, how many moles of chlorine are required to react with all of the iron? Okay, so 2Fe and 3ClO2. Cl2, excuse me, not ClO, Cl2. And then it produces 2 of those. Yep. Okay, so 6 of those, 6 and 2. Okay, that's balanced. All right, we're given 3.4 moles of iron. How much chlorine is required? Number of moles to completely react with that. Very simple. It's a simple conversion. Right, so we get rid of the iron and leave the chlorine. That's 3, that's 2. So 1.5 times that would be 3.4, and 1.7 would be 1, 4, 5.1 moles of chlorine. Right? C's the answer. You can use your calculator if you want. I just figured it was quicker to do it in my head. 72. Ammonia reacts with oxygen to form nitrogen dioxide and water. We've seen this reaction before. And this one is balanced. Reacts with oxygen, we're burning it. 7O2 yields, let's see, 4 of these and 6 waters. Yes, 6 waters. Okay, that's our balanced equation. You react, at the end of the experiment, you find you produce 23 grams of water. All right. And have 8.52 grams of ammonia left over. So we have 8.52 grams of ammonia is excess. So what probably happened was we ran out of oxygen. It was limiting. That means we had excess here. So the question is, what's the mass of oxygen reacted? what's the mass of this reactant? Well, we're saying that this is excess already. That means this is limiting. So the only purpose for this statement of that much left over is to tell us that this is limiting. We don't even need that anymore. Now that we know this is limiting, we can say, how much of that produces this? So 23 grams of water, we're going to convert to moles first, of course. That's 18.02 grams divided into 23. (1.2764) moles of water. Now we're going to convert that to oxygen. Water here, oxygen there. This is 6 waters and 7 oxygens. So 7/6 of that value. 1.4891 moles of oxygen were required. But the question is, what's the mass of oxygen required? All right, so we got to go one step further. That many moles of oxygen is how many grams? Right? Oxygen, 32 grams per mole, right? Because one oxygen is 16. Do the math. 32 times that. 47.658. Oops, that's not right. 6508. All right, we have 3 significant figures. So I got to go 48. I can do better than that. 48.0. Right? More than 5, round it up. That one becomes 0. This is grams of oxygen. All right, it says 47.7 grams of oxygen. Let me see if there's a rounding error in here. 23 grams here. Okay. 23 grams. Water. 16 plus 2.02. That's right. Oh, I think I know what happened. They probably used 18 here instead of 18.02. Let me see if that fixes it. So that's 1.2778 times 7 divided by 6 is 1.4907 is 1.4907 times 32 is 47.7. Yep. That's the difference. I used 18.02 and the creators of this problem used 18 only. So in that case, you use the answer, the best answer, and the best answer is 47.7. Okay. Well, we only got about 9 minutes left. Let me see. 73. Let's see how many more I've got to go. I may have to go over a little bit. Yeah, I got this one, 1, 2, 3, 4, 5. Got 5, including this one. So I'm going to pass 11 o'clock just a little bit. All right, for this reaction, C2H4, which is ethene. You don't know that, and you don't need to know that. Plus oxygen, which is a combustion reaction, yields carbon dioxide and water. So let's put that one up here. C2H4 plus oxygen yields CO2 plus water. Did they balance it for us? Yep. 3, 2, 2. 3, 2, 2. All right. If 5.5 moles of carbon dioxide are produced, how many moles of oxygen were reacted? This is too simple. Right? That's moles of carbon dioxide. We want to convert it to oxygen. So we have 2 here and 3 there. So 1.5 times that. I'm going to do that one on my calculator. 8.25 or 8.3 rounded off moles of oxygen. And let me see, did I do that right? 5.5. Yeah, 5.5 times 3 divided by 2, 8.25. Rounded off. Actually, since you have a choice, D is none of these, then you could technically say none of these. Right? So for the exam, what I need to do is stick something in there, because the best answer for this one, except for D, is C. Okay. Let's pick up 75. All right. Consider the following unbalanced equation. We balanced this one before. C2H5OH plus O2 equals CO2 plus H2O. And if 1.86 grams of ethanol, 86 grams of ethanol, reacts with 14.3 grams of water, of oxygen, excuse me, of oxygen, how many moles of water are produced? So we need a balanced equation. Let me see. I think there was a 3 here, and there was a 2 here, and there was a 6 there, I believe. Let's see. That would be 2 carbons, 6 hydrogens. We only need a 3 here. 6 hydrogens and 7 oxygens. 4 plus 3 is 7. There we go. Now we're balanced again. Okay, so what do we do here? Well, we've got 2 amounts here. We got to find out which one's limiting. So we got to convert this one to moles. And we need a molar mass again. So I'm going to do this one real quick. 2 carbons, 6 hydrogens, and 1 oxygen. So this is 4608. And that's divided into 1.86 is 0.0404 moles of ethanol, which we're going to go ahead and convert to water. So ethanol here, water here. 3 waters and 1 ethanol. So I need 3 times that value. It's 12.1. 0.1211 moles of water from ethanol. How about oxygen? 14.3 grams of oxygen. Convert that. 2 16s are 32. Yeah. So 14.3 divided by 32 is 4469 moles of oxygen. Now we're going to convert that to water. Right, so we have 3 of these, 3 of those. It's the same number, 4469 moles of water. That means this one is limiting. That's how many moles of water are produced. Rounded off to 3 places would be 0.121. Okay. Got that one done. Let's see. We're in the neighborhood of the 80s, I think, for the next one. There we go. Nitrogen gas reacted with hydrogen gas, determine the mass of ammonia that can be produced. All right. If you don't already have this one memorized, nitrogen gas reacts with hydrogen gas to produce ammonia gas. All right, so we need 2 here and 3 there to balance our equation. 22.5 grams of nitrogen. 22.5 grams of nitrogen react with 22.5 grams of hydrogen. I'm going to stagger them like that so I can just go ahead and string the calculation out. What's the mass of ammonia that can be produced? We need to find the limiting reactant. Okay. So we need to convert 2 nitrogens. 1 nitrogen is 14.01. 2 of them is 28.02 grams per mole. Right? So it gets rid of that. Now I'm going to go ahead and string it together. This is moles of N2. So I want to convert N2 to NH3. So we got 1 here and a 2 there. So I'm going to do it all in one calculation. 22.5 divided by 28.02 times 2 is 1.6060 moles of NH3 could be produced from that much. How about hydrogen? Well, in this case, grams per mole, hydrogen is 2.02 grams per mole because there are 2 atoms there. And then we're going to convert moles of hydrogen to moles of NH3. So there's 2 here, 3 there. So 2/3 of 22.5 is 15 moles of NH3. That means this one is limiting. That's actually how many moles are produced. So how many grams is that? 1.6060 moles. What's the molar mass of ammonia? Well, it's 14.01 for nitrogen and 3.03 for all of the hydrogens. So that's 17.04. Times, let's see, we do that, and then 17.04, 27.3662 grams, rounded off to 3 places, 27.4 grams of ammonia. That would be B. All right. We ought to be getting close. I'm just barely past, so let me see who's next. 83. Fe2O3 reacts with CO according to the equation. We had one that looks exactly like this one. At least the equation is the same. The conditions may be different. Fe2O3. Now that's an actual compound. We can name that one. That's iron 3 oxide. Reacts with carbon monoxide to produce carbon dioxide plus what? Plus iron. Let's see. 2 irons, 4 oxygen. Oh, 3 plus 3 is 6. 6 oxygens, 3 carbons. That's balanced. I'm satisfied. So when 470.0 grams, 470.0 grams of iron 3 oxide reacts with excess carbon monoxide. Okay. What number of moles of iron is produced? So in this case, we do need that molar mass that's given, 159.7 grams per mole. So we'll take this value and convert it to moles of Fe2O3. 159.7. So that's how many moles of Fe2O3 go into this reaction. And let's just string them together. This is moles of Fe2O3. So then we're going to convert Fe2O3 to Fe, which is 2 here and 1 there. Now we can do the whole thing in one calculation. 470. 159.7 times 2 is 5.886. Round it off to 4 places. That's it. That's moles of iron. 5.886. C is the answer. All right, we ought to be getting close to the end. 84. Couldn't be too many till we get to the end. 84. Yep, this is the last one. 84. Which of the following statements is always true concerning a reaction represented by the following balanced equation? So let's write that up there. 2C2H6, that's ethane, reacted with oxygen, 7 of them, to produce 4 carbon dioxide, is it? And 6 water. Okay. So which of the following statements is always true? Always true. Well, A says none of these are true. So we'll look at B. All right. If we have an equal number of moles of C2, H6, and O2, there's no limiting reactant. If we have an equal number of moles, right? Say if you have 7 moles of this and 7 moles of that. Okay, that's equal. We can pick any equal we want. There's no limiting reactant. That's false. Because you only need 2 of these to react with 7 of those. Okay, that's not true. How about C? If we have equal masses of C2H6 and O2, equal masses? Well, let's see. Let's just say, for argument's sake, we have 100 grams of each. Well, I'll do it down here. 100 grams. 100 grams. Right? So how many moles of C2H6 do you have? Well, we need to multiply that times the value that will cancel grams and leave us with moles. So we need C2H6, which is 2 carbons, 12.01 times 2, and 6.06 for all the hydrogens. So that's 30.08 divided into 100. There, 3.32. 3.32 moles here. How about this one? Oxygen, 32 per mole. So 100, enter, 32 divide, yields 5. Is that right? That's not right. That didn't make any sense. 100, 32 divided. 3.125. 3.125 moles. Okay. So we've got almost the same amount of moles, but for every 2 of these, you need 7 of those. So who's going to run out? Well, if this represents 2, then 1.66 here would be related to what? 7 of, let's see. One of those requires 3.5 of these. So one of these makes that many. This one's going to run out first. Right? So that statement's false. D, if we have more mass of O2 than C2H6, must be the limiting reactant. All right, let's do it this way. Suppose we still have, our starting point is equal masses. Right? So this mass of C2H6, how much mass of O2 do we need? So we have 7 divided by 2 equals, let's see. Let me just do it this way. You need 11.6 moles of oxygen. So if you have this many moles, if they're equal masses, 100 and 100, equal masses, you need that many moles of oxygen. Right? So oxygen is going to be limiting, yes, you only have 3.125 moles of oxygen. Oxygen is going to be limiting, right? We compare this one with that one for this many moles of C2H6. So oxygen is going to run out first. All right. If you have more mass of oxygen, you could catch up a little bit. But this one is still not going to be limiting. It's always going to be this one limiting until you get to 11.6 moles with that many moles. So this one is also false. It says that C2H6 is limiting, right? But oxygen is limiting over a wide range. Right? So how about E? If we have more mass of C2H6, right? If we have more mass of this than O2, then yes, oxygen's limiting. If they're equal masses, it's limiting. So more mass of C2H6 is still going to keep oxygen limiting. That is true. E is the only true statement out of that bunch. And I believe that's it for our review. Yes. Let's see. There we go. Got hung up for a minute. Okay, so that's it for our review. And the exam will be due by 11:59, next Tuesday.